In this video, we're going to take a look at section 1.2 on types of data or data. So a lot of the concepts in this section, I like to call them verses. There are basically two versions of the concept, and a lot of the problems are going to be you choosing which version is appropriate for the given description. And so in this case, for example, we have parameter versus statistic. A parameter is a numerical calculation describing some characteristic of a population. So reading that sentence, it's hard to tell where the emphasis should be, but it should be on population. Right? I didn't do a very good job with that. Let's try that again. I was going to say maybe I should use the highlighter tool, but I don't want to mess with a whole other thing. So a parameter is a numerical calculation from a population. That's what distinguishes it from a statistic, which is a numerical calculation describing some characteristic of a sample. Right? So remember in the previous video, section 1.1, we talked about the difference between a population and a sample. So a population is the entire set of the thing that you're studying. A sample is a subset of that entire set of the thing that you're studying. And like I said, for most scenarios in this course, and when I say most, I mean like 99% of the time, we will be working with samples because collecting data from an entire population is often impractical and maybe even impossible. So we're normally going to be working with samples. So most of the calculations we do in this course will be statistics and not parameters. But the statistics we are calculating, we hope, are representative of those parameters. So when we get a sample and we measure the mean, or we calculate, maybe measure is not the right word, we calculate the mean of that sample, we hope that it is representative of the mean of the population. So we hope that our statistics are good estimates for these parameters. We want the sample mean to be a good estimate for the population mean. All right. Okay. Qualitative data consist of measures that are names, labels, or other descriptive terms. So these are, for the most part, non-numerical measurements, non-numerical data, observations. There are a couple of fringe cases where you have to be careful because numbers might be used, but not in a numerical way. So I'm going to save that example for later. I want to talk about it now, but I have it in an example later in the video, so I'm going to try to wait to talk about that more. But essentially things like colors, sizes maybe, like if you're measuring the size numerically, obviously that's not qualitative, but if it's like small, medium, and large, right? So French fries at McDonald's, right? Small, medium, large, that would be qualitative descriptions, right? That's not quantitative. What's another good example? I can't seem to think of anything off the top of my head. But just anything that uses words essentially would be qualitative data. And maybe we'll see some better examples later in the video. And I'm sorry, I think when I recorded the video for 1.1 or all the previous videos I've recorded, I've said data, data, data. Now I'm saying data, and I'm having trouble deciding which way to say that word today for some reason. Quantitative data, on the other hand, consist of numerical measurements representing counts and measurements. That's a little bit repetitive there. I didn't catch that the couple of times I've read through this. But again, we have to be careful because sometimes numbers can be used as labels. And if the numbers are being used as labels, then it's qualitative data, even with numbers being involved. So these have to be numbers that are doing number things. They're not being used as a label. They're being used to count or to measure or whatever else you might use numbers for. All right. So that's quantitative data. Now, quantitative data can be further described by two different subtypes, either discrete data or continuous data. And these further describe, again, this is another verses, right? We have qualitative versus quantitative. So let's go back. We have perimeter versus statistic. We have qualitative versus quantitative. Now we have discrete versus continuous. But discrete and continuous only apply to quantitative data. We cannot use those labels for qualitative data. So the difference, and this is a hard one for students to kind of wrap their mind around, discrete data versus continuous data. Discrete data result when the number of data values, so there I'm sorry for the inconsistency, it might drive some people crazy. Discrete data result when the number of data values, what did I say here? Result when the number of data values are finite or countable. Okay, I guess that makes sense. Now I'm kind of questioning my wording there. Result when the number of data values are finite or countable. So finite is the opposite of infinite. So it's kind of amusing to me when students see that word. They don't really recognize it, but it's just the opposite of infinite, even though you kind of say it a little bit differently. You say it as finite. So for example, if we talk about the age, maybe age is a little bit of a tricky one, the number of movies at the movie theater, right? That is finite. There is a limited number of movies that can be shown at a movie theater at any given time, right? So either there's one movie, there's two movies, or if the movie theater's shut down, like maybe it is right now, there might not be any movies, right? It could be zero. So it could be as low as zero. It could be as high as the number of theaters within that movie theater. So maybe it could be like up to 8 or 10 or 22, depending on where you live and what kind of movie theater you have access to. But it's limited. It's finite. Countable means could be finite, right? The number of movies at a movie theater is countable because it's limited. But countable can also be infinite, but it's, and this is kind of a crazy mathematical concept, there are different levels of infinity. Greg or Gregor, I can't remember, maybe it's Gregor. No, that doesn't sound right. But Cantor was his last name. And he spent time studying infinity and different levels of infinity. And I haven't researched this, but my recollection was like he kind of went crazy. And the other thing was people just thought he was wasting his time and was being silly and didn't believe him, which probably drove him crazy. But it turns out his work was actually quite valid. There are different levels of infinity. And there's countable infinity and there's uncountable infinity. And it goes even further than that. But countable infinity would be like 0, 1, 2, 3, 4, all the way, like forever. And so you might have a data set where there's no actual limit to how far it could go. But if it's counting numbers only, even if it can go forever, that's still considered discrete data. All right, so that's what countable means there. That it might be infinite, but it's countably infinite. Data that can only, so let me read. I'm having trouble for some reason thinking about my words today. Data that can only be integers or with limited decimal places would be considered discrete data. So another example that I like to give, because many students are trying to simplify these concepts to make it easy for them to get the right answer on the test. And a lot of people will simplify discrete data to just if it's a whole number. If it's a number that I count with and that's all it can be, that's discrete data. But money is another example of discrete data. Even though money goes to 2 decimal places, it's still considered discrete because it's countable. Even though it might be infinite, right? It might have an infinite amount of money. It can go, there's no limit to how high up the amount of money you have, even though technically there is, because, right, there's only so many dollars printed in the world, even though money now isn't necessarily based on the amount of print money, but like it's kind of electronic now. So really, in theory, there's no limit to how much money you might have. So it could, there's no limit, which kind of makes it infinite, but it's still countable, right? And so that would be considered discrete data. Continuous data, on the other hand, result when the number of data values is uncountably infinite and exist along a connected spectrum of possible values. So it has to be connected. There can't be gaps, basically. So one way I try to help students understand the difference here is that with discrete data, there are gaps. Either there are 8 movies showing at the movie theater or there are 9. There's no in between. You can't have 8.5 movies, right? And so there's a gap there between 8 and 9 where numbers exist but aren't possible data values in that particular situation, right? Whereas continuous data does not have gaps. So an example of continuous data would be to measure the heights of people. Now, again, we often will describe our heights in a discrete way. We'll say, I'm 5'10", for example. But in theory, I could measure it more precisely than that. I could say that I'm 5.87239, not 10, 397, I could keep going, right? In theory. So if I had equipment that was precise enough, in theory, I could measure my height to however many decimal places I want. And so data that could, in theory, be measured to an arbitrary number of decimal places are continuous data. So that's what you want to look for with continuous data. Could I, not that it is being measured to that many decimal places, but in theory, could something like that be measured that many decimal places? If so, it's, not that many, but just however many you want. If in theory you could measure it to whatever degree of accuracy that you wanted, whatever degree of precision you wanted, with as many decimal places as you wanted, that would be continuous data. Discrete data has a limitation at some point. All right. So that's the difference between discrete and continuous. We'll do some examples later, and hopefully you'll get a chance to practice telling the difference. Levels of measurement. So there are 4 levels of measurement that you need to know. Nominal, ordinal, interval, and ratio. Nominal data is data with no ordering. These will often just be your qualitative data, but I suppose some qualitative data could be ordinal as well. So it's not just exclusively, how do I want to say this? Qualitative data is not just exclusively nominal, but nominal data, I think, is pretty much always qualitative, if that makes sense. And if they cannot be arranged in some sensible order, and I'm not talking about alphabetical order here, I'm talking about like some logical order. We'll see some examples later. Ordinal is data with ordering possible, but where taking differences would be meaningless. Now, a difference, remember, in math is subtraction. So if you could not subtract the data in a meaningful way, that would indicate that it's ordinal. You can put it in a certain order, but subtracting 2 data values in that data set wouldn't make sense. That's what makes it ordinal. So a difference would be to subtract. Interval is data with meaningful differences. So this is data that can be ordered. So there's a hierarchy here. It's data that can be ordered with meaningful differences, but no natural zero, where the zero in that data set is kind of arbitrary or can be sort of defined wherever you want to put it. And then ratio is data with meaningful differences and a natural zero, a natural starting point. And that's what makes data a ratio. So again, we'll see some examples later, and I'll maybe expound on this a little bit more. So right now, maybe that's a little bit fuzzy, a little bit abstract. But when we get to some examples, hopefully that'll clear it up for you. But for now, I'm just going to kind of leave it as these definitions. All right, so let's take a look at some problems. Determine whether the given value is a statistic or a parameter. So remember, the key difference between statistic and parameter is that a statistic is a calculation from a sample, and a parameter is a calculation from a population. So in a AAA Foundation for Traffic Safety survey, 21% of the respondents said that they recently texted or emailed while driving. Right? So this was a survey which presumably was not collected from every driver. Right? So for this to be a population that we're talking about, the survey would have to have reached every driver, and every driver would have to have responded for it to be considered data from a population. So surveys are generally regarded as, data collection from a sample, and that it's not reaching every person in the population. So because I don't see language, and sometimes these problems are a little bit subject to interpretation. So you could read further into it and say, well, maybe it was sent out to everybody, and maybe this 21% is data that was calculated from everybody that drives. But if it doesn't explicitly say something like that in the problem, you shouldn't assume that to be the case. So what I usually tell students, because sometimes students get bothered by this because they do these hypotheticals. Well, hypothetically, this could have been the case. Don't do hypotheticals with these problems. Only go with what's actually explicitly stated in the problem. And if it doesn't explicitly state that everybody in the population was part of the data collection, then it's a sample. And if it's a sample, it's a statistic. Right? So this would be a statistic because this survey was sent out to a sample of the population and not the entire population. Just to kind of, drive that point home, I think this next example illustrates it pretty well. Right. A study was conducted of all 2,223 passengers aboard the Titanic when it sank. So if the situation involves the entire population, they will put some obvious language in the problem to make that clear. And even though it doesn't use the word population here, it says all. Everybody that was part of what was being studied was part of this study. That sounded kind of funny to say. So everybody who was being considered in the study was included with this particular data collection that they were doing. And that was indicated by the word all here. So that means that this study included everybody in the population, which means that whatever calculations they do here would be parameters. They would not be statistics in this case because it involves the entire population, and the word all indicates that. So if they say something like everybody in the study group was included in the data collection, that's a population. Everybody, all, you want to look for keywords like that. And again, don't read further into it than just what's given in the problem. You just want to base it on what you actually were given. All right, determine whether the given values are from a discrete or continuous data set. The Honda Civic has 4 cylinders. So what you want to ask yourself to determine if this is discrete or continuous is, could I take that measurement and measure it to an arbitrary number of decimal places? Or are there gaps in the measurement where it wouldn't make sense to have more decimal places? And for the number of cylinders in a car, there's a gap. You either have a 4-cylinder engine or you have a 5-cylinder engine. You can't have a 4.3278 cylinder engine, right? It's a counting. So if you're doing counting with the data, it's discrete. If it's any kind of counting at all. So you're counting the number of cylinders, it's discrete data. So this is counting. And it wouldn't make sense to try to measure it to more decimal places because you can't have decimal places on this kind of data, right? It wouldn't make sense to have 4.5 cylinders, for example. So it's counting, it's discrete. All right, George Washington was 188 centimeters tall. Now, while that is a whole number, that doesn't mean this kind of data is discrete. Could I have measured, could people's heights, right? We talked about heights already. I kind of gave this one away. But could that be measured to more decimal places if we wanted to, in theory? Yes. It makes sense to say George Washington was 188.1 centimeters tall, right? If we wanted to measure it more precisely, we could. And we could go more than one decimal place. We could say George Washington was 188.13 centimeters tall. And if we wanted to be more precise, if we got better equipment, we might be able to say George Washington was 188.132 centimeters tall. We could go 3 decimal places. We could go 4. So there's no limit to how many decimal places I could carry out this measurement. And so this is continuous. So it's again, you could think of it as being along a spectrum of possible values, right? And so it's continuous. All right, so we could go more decimal. I want to write it out on the screen, but I don't want to take the time to do it. So we could measure this to an arbitrary number of decimal places. Just because they decided to make it a whole number measurement doesn't mean it was forced to be that way because of the nature of the measurement. Whereas the 4 cylinders, it's forced to be a whole number because of the nature of that measurement. So that's another way maybe to think about it. All right. Determine which of the 4 levels of measurement, nominal, ordinal, interval, or ratio, is most appropriate. The colors of M&Ms. So whether an M&M is red, orange, yellow, blue, brown, or green, there's no way to order those colors. Now you might say we could do alphabetical order, but that's not really a logical order to this data. reason, like there's no, I don't know how to explain it, but there's no logical ordering there. It's just sort of arbitrary based on, we call the color blue blue, but we could call it a different name, right? We could have azure, right? And then that begins with an A, and that might put it in a different spot in the alphabetical ordering. So these are just labels, and ordering it by the alphabetical order of the labels is not really a very logical ordering because the labels we give it are somewhat arbitrary, right? And so if we used a different name for that color, it would put it in a different order, and it wouldn't matter to the data which order the colors were in. And so there's really no ordering to be done with colors. This makes this measurement nominal. It is qualitative data. There's no order that we can really apply to this data. It doesn't matter, the order that we list the colors in. Depths of earthquakes. So depths definitely do have an order, right? It makes a difference whether the depth was 100 kilometers or 1,000 kilometers. And there's a natural order, a logical order to depths, right? Not only that, but depths have a natural zero, right? So the surface would be 0 for the depth, right? So there's a natural starting point from which to measure the depth. Differences between the depths make sense, right? So if I have 1,000 kilometers versus 100 kilometers, I can subtract those and I can find the difference in those depths to be 900 kilometers. So there is a meaningful difference to be taken there. So we have a difference, there's an ordering to it, and there is a natural 0 starting point. That makes this a ratio measurement, right? It's a ratio. The level of measurement here is ratio. All right, so it has to check all those boxes. Ordering, difference, meaningful difference, and a natural 0 starting point. Years in which U.S. presidents were inaugurated. So this one has an order to it, right? Years definitely have an order. There's a logical way to order the years, right? So 2019 comes before 2020, right? It makes sense to order them in that way. Differences make sense with years, right? So, if we look at the year 2020 versus 2010, we can take that difference and we get 10 years. So the difference between those two data values is 10 years, and that's a meaningful difference, right? So we can subtract and have a meaningful difference. So there's ordering, there's meaningful difference, but is there a natural 0 starting point? This one might be kind of tough to figure out because we do start a numbering of years at a certain point in history, but that's kind of arbitrary, right? There's no reason why it had to start in that particular year. And so we could measure the number of years since the, Declaration of Independence, for example, which was 1776. And so we could say it's year 243 now relative to the year the Declaration of Independence was signed. We could measure the number of years since the year 2000 if we wanted to. Now it's year 20, right? So where we start measuring the years, there's not a natural automatic place where that should be done. So it's sort of arbitrary, and we have to kind of decide what we think year 0 should be, but that was kind of up to us to decide. There isn't a natural place to put that. Whereas for depths, the surface is obviously the natural point where 0 would occur. You don't really get to choose that. That's just where it should be based on what depth means, right? It's how far below the surface. So the surface would have to be 0. There's no choice in that. But for years, we have a choice. Now, we tend to, we sort of are, historically, we have chosen to let the birth year of Christ be the 0 starting point. And maybe for some people that is the only logical choice, but we could measure number of years from other reference points, right? And so this is interval measurement. It doesn't have a natural, automatic 0 starting point that's beyond your choice, right? We get to choose that 0 starting point. Another example of interval measurement that you might be interested in is, and another way, this is another good way to think about it. Does 0 mean none of it, right? So if year 0 doesn't mean you have no years there. It's just, that's where we decide to start measuring, our years. 0 depth means there's no depth there, right? So if 0 actually means none of that thing, that's an indication that it's ratio level. If 0 does not indicate none of that thing, that's an indication that it's interval. So another good example would be temperature, is what I was about to say. So temperature, again, 0 degrees is a little bit arbitrary. You know, you can define 0 degrees to kind of be whatever you want. Now, a really sensible way to define that would be to let 0 degrees be the freezing point of water, right? That's a good thing to let it be, but that's what they do for Celsius temperature scale. But for Fahrenheit, 0 degrees actually doesn't really have any like good, associations. It's a little bit arbitrary what 0 is for Fahrenheit, right? I think it is. I don't know. Am I thinking of it the right way? Yes, I think so. I don't know. Yeah, that's kind of, is there? I don't know. I'm trying to think, what are the reference points for Fahrenheit? I can't remember. But in order to invent a temperature scale, you need 2 reference points two reference points that you have to define 2 different temperatures. And then from that, you can create a temperature scale. So for Celsius, the 2 reference points are the freezing point of water, which we define to be 0 degrees, and the boiling point of water, which we define to be 100 degrees Celsius, right? And of course, that's at, sea level and all that stuff. And so from there, you have a temperature scale called the Celsius temperature scale. But Fahrenheit uses 2 different reference points that I don't remember what they are. And so we get a slightly different scale. And 0 degrees in Fahrenheit is different than 0 degrees in Celsius, right? And so where 0 degrees occurs really is arbitrary. For the Kelvin scale, 0 degrees is actually absolute 0. It's the lowest temperature that is possible. So this one's kind of a little bit weird, which again might make sense, but we could define 0 degrees to be something else. So if the temperature outside is 0 degrees, does that mean there's no temperature outside? No. So again, 0 in the temperature scale doesn't mean there's none of that thing. And so therefore, temperature is an interval level of measurement. All right, so hopefully that makes sense. The movie Avatar was given a rating of 4 stars on a scale of 5 stars. So this one, there is an order to it. So it's not nominal, right? Because 4 stars is a worse movie than 5 stars, right? A 3-star movie is worse than a 4-star movie. So it makes sense to order the ratings on a scale, right? 0 being the worst kind of movies and 5 being the best kind of movies, right? So there's an order to these ratings. So it's not nominal. There's a logical order to it. But are there meaningful differences here? Meaning if I take 2 ratings and subtract them, does that subtraction tell you anything? And the answer is no. So what is the difference between a 4-star movie and a 2-star movie? If I subtract those stars, 4 stars minus 2 stars, I get 2. But does that tell you anything meaningful about the gap between a 4-star movie and a 2-star movie? No, not really, right? So differences in the number of stars that we rate movies don't really tell you anything about the differences in those movies. And so there's not really there's no meaning behind taking the difference between the number of stars a movie was rated. And so this is going to be the ordinal level. Right? There's an order to it, but differences between the measurements are not well defined. All right. Okay, so determine whether the data is qualitative or quantitative. And this is the end of the video. This one's actually a very short lesson. Unfortunately, I just warned you because I actually already recorded the Chapter 2 and Chapter 3 videos. Those get pretty long. I don't know why, because I feel like when I teach it in class, it goes quicker than what it did in the video. So I apologize. I got a little bit verbose in those videos. Determine whether it's qualitative or quantitative. The number of cars in a Walmart parking lot, it's a counting thing, right? We're counting the number of cars. It's a numerical measurement. And so this is quantitative. I'm just going to abbreviate quant and qual, I think. The color of the cars in a Walmart parking lot, well, we already kind of talked about colors being qualitative, right? It's a label. So qualitative for the color of the cars. The cost of making a movie. Well, cost is a numerical measurement, right? You're measuring the amount of money that it took to make that movie, And that measurement it's a counting thing, right? You're counting how many dollars were spent to make that movie. And so this is quantitative. The runtime of a movie, also quantitative. Now, the reason I put those two examples here, so they're numerical measurements, is I wanted to talk about discrete and continuous again, right? So the cost of making a movie, is that a discrete quantitative measurement or is that a continuous quantitative measurement? Now, again, cost can be measured to two decimal places, right? We could say this movie cost $1,328.32 to make, right? It's a really cheap movie. So you could go decimal places on it, but I mentioned it already. I kind of gave this away earlier in the video. This is a discrete measurement, even though it has decimal places, because it's still limited to two decimal places. So there's a gap, right? Either it cost $5.38 or $5.39, right? And there are numbers between 5.38 and 5.39, right? There are numbers between 5.38 and 5.39, like 5.385, right? That's between those two numbers. So their numbers exist there. There's always numbers between any other two numbers. But that particular number, 5.385, is not a possible data value when you're talking about cost. So there's a gap where numbers exist but cannot be possible data values in our data set, and so that would make it discrete. All right. The runtime of a movie, however, is continuous. Now, this one can bother students as well, and I know this because when I teach it in class, I'll ask my students to answer first, and I'll ask for maybe a show of hands or something, and half the class will say it's continuous, half will say it's discrete. And when you have a discussion about it, students will say, well, when you look at the runtime of a movie, like on Netflix, it'll say this movie is 1 hour and 38 minutes. And this movie is 1 hour and 52 minutes, right? That appears to be discrete because it's limited, like it's either 1 hour and 52 minutes or it's 1 hour and 53 minutes, and it's never in between. And so that's how Netflix presents the data. But in theory, could you measure the runtime of a movie more precisely than that? Could you use some decimal places to say it's 1 hour and 52.3872 minutes? Yes, you could. If you wanted to measure the runtime to 5 decimal places, you could. You could measure it to 10 decimal places. And so that makes time a continuous measurement because you can, in theory, measure time to a very, very tiny degree, right? You can measure it to microseconds, femtoseconds, whatever, however, now there are limits, then you start getting into quantum stuff. So yeah, there are physical limits there as well. But mathematically speaking, you can measure it to an arbitrary number of decimal places if you had the technology to do so, which makes it continuous. Now, Social Security numbers, would that be qualitative or quantitative? Now, these are numbers, but Social Security numbers are actually qualitative data. It's like having a name, right? There's my name, and then another label the government gives me is my Social Security number. The number itself is kind of meaningless. It's a number that's really given to me to label me. It's not a number that works like a number does. If for example, if you take two Social Security numbers and add them together, is that a meaningful thing to do? Of course not. It would be, it would tell you nothing about anything, right? It's just nonsense to add two Social Security numbers together. So they're numbers, but they don't act like numbers, right? Because numbers you can add together, right? Kind of like the 4-star and 5-star rating stuff, right? Can you add those numbers together? Well, not really. It doesn't really make sense to do that. So rating a movie 4 stars or 5 stars is really a label that we're giving the movie. It's not really quantitative data. It's more qualitative. So same thing with Social Security numbers. So a good way to kind of check for that is, can you do number things with those numbers? Can you add them together? Is that a meaningful thing to do? Can you subtract them? And if the answer is no, even though it's numbers that are being given to you, if you can't do numerical things with those numbers, then those numbers are probably more labels than they are actual numbers, and so, which makes the data qualitative rather than quantitative. So that's just kind of an interesting fringe case to consider. I don't know why I'm writing this word all the way out, but qualitative for Social Security numbers. So that concludes the video for section 1.2. Thank you for watching, and I will see you in the next video for section 1.3.